Okay, it's time to move on to dipole interactions. So we just talked about dispersion forces. So let's talk about dipole interactions. Okay. One thing we need to think about is this molecule polar or not? Is there a dipole or not? That's an important piece of information here. So let's look at a couple examples to figure out where they would fit. Let's look at an example of, say, no, let's not do that. Let's do something like CH2O, formaldehyde. So in formaldehyde, if we sketch this out, we have a couple different bonds to consider. We have the CH bond and we have the CO bond. This CH bond, in the bond polarity video, we talked about how that was nonpolar. Now the CO bond is a polar covalent bond, so that is a polar interaction. When we look at the entire molecule, we see that right here is where that polar interaction is going to come from. And in this case, the oxygen is more electronegative than the carbon, and so it's going to pull the negative charge up here. So we're going to get our partial, here, I'll redraw that. We're going to get our partial negative up towards the top, and down here our partial positive down here. Therefore, this molecule is a polar molecule, and if it's polar, that means it has a positive end and a negative end. Therefore, it has what we would call a dipole. It has two poles. Because it has a positive and negative end to it, it has a dipole. So dipole interactions occur between molecules that have dipoles. Now, it could be the same molecule, or they could be different molecules, but in this case, what happens is we might get a molecule of formaldehyde next to another molecule of formaldehyde, and based on where these centers, these areas of positive and negative charge are, we're going to get these interactions. So we're going to get this negative area of this oxygen, being attracted to the positive area around this carbon. Now you get enough of these together, and you're going to start seeing lots of these interactions. So we might have, for example, a carbon here, and an H, and an H, an O, and we might have this kind of interaction here, this kind of interaction here as well. That interaction is stronger than dispersion forces. Remember, dispersion forces are caused by these slight shifts in the electron clouds. Those are called induced dipoles. I'm not sure I said that in the last video. They are called induced dipoles. We could also think of them as temporary dipoles. Now, dipole interactions are between molecules for which there is a permanent dipole. And they are stronger in interaction than the London or dispersion forces. All right, so our final type here is H bonding. Now, H bonding is going to at first sound a lot like dipole interactions. It's just a special case of a dipole interaction. It's one that's exceptionally strong, and it has earned its own category. So to have H bonding possible, this might be an oversimplification, but it gets to the idea. down. So this occurs, so in polar molecules, where H is bonded to one of 4 atoms, is bonded to, usually it's nitrogen, oxygen, fluorine, or chlorine. So H needs to be bonded to one of these 4 here in order for H bonding to occur. Again, a little bit of a simplification, but it'll help you to see where this can and can't happen. And it's a pretty good rule. It works most of the time to look for N, O, F, or Cl. Those are the 4 most electronegative elements. Okay, so classic example of this is water. So we have water. This might be easier to see if we draw this 3-dimensionally a little bit, show some of that bent structure that water actually has. So the drawing dot structures and knowing molecular geometry is paying off as we look at this. So what we know is that the HO bond is a polar bond. Okay, the O is much more electronegative than the H. It's got an electronegativity near 3.5, and H was at 2.2. We can write that in. So 3.5 and 2.2. That's actually a pretty strongly polar covalent interaction. As a result of that, in the interaction, it's wanting to type. That means we're going to get a negative here and a positive here between these two, but we're also going to get a polar covalent interaction here. And so water, as a result, down here at this end of the molecule, is much more negative than it is over at these 2 ends, really 2 ends, where it's much more positive. Okay, now it's not; those aren't complete charges. It's not an ion, but it is significantly polar covalent. So if we get a couple water molecules next to each other, we get these things. We're going to do this one way. We get these things interacting. I've omitted the lone pairs of electrons. I'm assuming you know they're there. And so we get this negative area of this oxygen attracted to the positive area of this water molecule over here. We're going to get this attracting. We get these attracting, and you get the idea. So the positive areas are attracted to the negative areas of neighboring molecules. This is a stronger interaction than these dipole interactions, which, and they're stronger than these dispersion forces. So H bonding is the strongest of these 3. The next step, if you're going in strength of interactions, you'd get to ionic bonds. All right, so let's look at an example, where we take a molecule and we're trying to work out what are the intermolecular forces acting between particles. So let's take, for an example, HCl. So we have HCl. What are the IMFs here? Okay, so we just draw this really simply. We get HCl. That HCl interaction, let's see, this has an electronegativity value of about 3.5, somewhere in there. And this is 2.2. So this thing is polar. If that's polar, that means we're going to get more negative over here, since it's more electronegative. It's going to be slightly positive over here. And so this molecule, my finger keeps hitting that button. This molecule is polar. So Is it polar? Yes. Because right here we see it's more negative on one side, more positive on the other. There's an imbalance in charge, therefore the thing is polar. Do we have H bonded to H bonded to NOF or Cl? The question we're really asking is, can an H bond? And the answer is, of course, yes. Oh. Yes. So when we're looking at the types of bonds that can form here, are the van der Waals interactions, we would say H bonding. Okay, let's look at one more example. Example 2, let's say we have CF4. So if we draw this, we're going to put carbon as a central atom. And just to get a handle on the structure, I'm going to draw it this way. And so we get this. Note we have a tetrahedral geometry. So if I draw this, maybe a little bit more reflective of this, I'm not going to draw all the electrons on here, but we saw them on the dot structure. Okay, we get this kind of structure. Now those F's are evenly spread out around that carbon. The CF bond, carbon, if we go back up here and look, do we have this on this one? Yeah, it has a value. It must have been on the other page. So carbon has an electronegativity of 2.5. We can look that one up. Electronegativity of carbon. Yeah, it's about 2.5, 2.6. Put 2.6. And fluorine is 4.0. That means that this covalent bond is polar. Is a polar covalent bond. And as a result, we're going to get slight negative, slight negative, slight negative, and slight negative at each fluorine. And there's going to be a pretty significant, I'm not talking, it's wanting to do that, okay? Pretty significant positive charge in the middle there. But because none of these fluorines here is pulling more electrons in that direction compared to any of the other directions, the overall, there's not an overall like center of negative charge that's different than the center of positive charge. In other words, there are no poles that are forming. Because if you map, and I'll use red for this, the center of negative charge, because these fluorines are all pulling evenly in, directions that are spread out evenly around the carbon, that center of negative charge is right in the middle of the molecule. And I'll use gold for this. That center of positive charge is also right in the middle of the molecule. So when you overlap these centers of positive and negative charge, you don't have poles, you don't have separation. So even though we have polar covalent bonds here, there is no separation of the poles. Therefore, this molecule is, as a whole, a nonpolar molecule. And if it's a nonpolar molecule, you only have dispersion forces. All right, I think that's going to wrap it up for this video.